Okay, so today in chapter 7, we're going to talk about the standard normal distribution. Okay. So remember last class, we talked about the normal probability distribution, and today we're going to look at what we call the standard normal. The standard normal is when we have a mean equal to 0 and a standard deviation equal to 1. The mean, we use the notation mu, right, for our population mean, and sigma for our population standard deviation. The mean is our center of our distribution, and sigma, our standard deviation, is the spread of our distribution. Sorry, this is like not focusing very well today. Oh, that's a little better. Okay, so last class we talked about the normal probability distribution, and we said, okay, we have the mean at mu and the spread at the standard deviation sigma, and I said too, it may change. Here, we're already going to see where it's changing. The mean is always 0, the standard deviation is always 1. The notation for this is Z follows a normal probability model with a center of 0 and a spread of 1. So let me write down what all this means. So first of all, we have Z here today. Last class we had X. Z, you should think about Z-score. Remember we talked about Z-score back in chapter 3? That was my data value X minus my mean divided by my standard deviation. The Z-score told me the number of standard deviations a value, which is X, is from the mean, right? So it told me how many standard deviations we are from the mean. If it was positive, it was above. Negative meant it was below the mean. And that's from chapter 3. So this is going to tie in here in chapter 7. So what this does is this standardizes it. It's just in the name here, this standard. So if we think back to the example from last class, and we looked at the height of all the students, right? Think about maybe it's not fair to consider the height of females to the height of males. And so maybe we want to consider separating them out and standardizing them so we can compare apples to apples. Okay, that's the kind of thing the standard normal does. And that's why we bring the mean to 0 and standard deviation to 1 by calculating the Z-score. Okay. All right, so let me just write what some of these things mean here. So 0 is always the center of my standard normal, and 1 is always the spread of my standard normal. Z is the key here. Okay. And remember, the N right here stands for normal probability model. Okay. All right. Let's take a look at some more notation. So, you know, when we calculate the probabilities, we say, like we did last class, where we write the notation of the probability form. So if we have, trying to overlap this here, the probability, and if we're looking at Z today, maybe A is my lower bound or my lower value is less than or equal to Z, which is less than or equal to my upper bound, B. And if we're calculating this probability, we're going to do the same thing we did last class. So with our calculators, we will use the normal CDF function. And the input will look like this. My lower bound, which is same as last class, my upper bound, just like last class, and the center, 0, and the spread, 1. When we're looking at Z, the standard normal, those don't change. Okay. We also have the percentile. So if we're looking at the percentile of Z, same thing again as last class, inverse norm calculator function. And you're going to put in the area to the left of the data value you're interested in. And again, center, 0, spread, 1. So this is what you're looking at when we have our calculator functions, and this is how you write it out. We don't really have like a specific form to write out percentile of Z. We just kind of more write it like a statement instead of like a probability format. Okay, so these are the same as last class. It's just now you're using 0 and 1 for center and spread. If you use Minitab, you may have noticed, and if you've tried it already, that 0 and 1 automatically pop in there for your center and spread. And for last class, you would have had to change it to whatever your mean and standard deviation were. Okay. All right, so let's take a look at the example. Let me just write this in here. These are from my calculators. That one and this one for calculator. Okay, let's take a look at the same example as last class. So for last class, we were looking at the student height. And we had our curve, so I'm going to draw it out. I'm having a hard time drawing a straight line today for some reason, so I apologize for that. It's on an angle. That's okay. We get the idea. Remember the center of my curve of all the heights, 68 was the mean. And then my spread was 2.5. So if I just write this curve out with the 3 standard deviations above and the 3 standard deviations below, I'm just going to fill them in. This is what we did last class. Okay, and this represents my random variable X, which was the student height, right? Now, today, if we were going to look at this same data, but if we standardize it. So if we take the same data, we're going to standardize this and bring it down to a 0 mean and a standard deviation of 1. What our scale would look like, and I'm just going to drop below here, the scale would look like this. My center is 0. And I would still have 3 standard deviations away. It's just now my standard deviation's 1. So I'm going to have -1, -2, -3 on this side. And these will be my Z's. Okay, and the curve would look exactly the same. And I can find probabilities exactly the same way. Okay, I can find percentiles exactly the same way. So just keep in mind that when we do this, what's important to notice is the Z. So if you had a problem and I just gave you the notation, I didn't explain anything, and I said the probability A is less than Z and Z is less than B, when you see a Z here, you know you're on this blue scale here. Okay. If you were to have an X here in the middle, then you know you're on the black scale, X. Okay, so the Z means a lot to us. Just having that Z right there, you should automatically think standard normal, okay? All right, so I want to talk about the Minitab stuff just for a second. And I just want to address what it looks like with the Minitab real quick with some of these problems. And of course, if anyone is using Minitab and they want extra instruction, you know, feel free to reach out. I'm happy to do so. But the Minitab and the calculator instructions, I typed up a separate document, and it's where the syllabus is located. And then I also put it on the first page of our team assignment today. So it's in 2 different places. So if you're looking at Minitab here, and we want to maybe calculate the area or the probability between these 2 lines, okay? So I'm not going to put any numbers in, I'm just going to put colors. When you use Minitab, Minitab asks you for the center and the spread, which is fine, okay? We're not surprised at that. Then, but what happens is it asks you for 1 data value. And you're going to put this data value in here that you're interested in. And it will, in return, give you this area to the left of that data value. Now, I don't want to know the area to the left of that, right? I want to know this in between. I'm getting there. We'll get there. Next, I'm going to take this blue box, this blue value, and I'm going to go back into Minitab again, and I'm going to put that in, and I will get the area to the left of that value here. So when I'm looking at that, I get this big chunk. So what happens is I'm going to take the probability that I got from the blue square, and I'm going to subtract the probability that I got from the black square, and I'm going to end up with this probability in between the 2. And that's what I was looking for. So all I'm getting at is you have to do this subtraction yourself. With our calculators, the calculators do it. We give it the 2 values, it will calculate in between. Minitab doesn't do that for us. Minitab always just gives this area to the left. I have to do the subtraction. So I just wanted to go over that in case the instructions weren't so clear on that part. But Minitab is very similar. You're still going to use the normal CDF function. If you're doing the percentile, you're still going to use the inverse norm. It's just the option right below it on Minitab. It's right there. You could just check that little box. It says inverse. And you know, same thing. You're just putting in the area to the left. So they're very similar. It's just with Minitab, I have to actually do the subtraction myself. And that's okay. We could do that. All right, so I just wanted to mention that and talk about that a little bit. But like I said, the instructions are all out there, and feel free to reach out to me, even if it's when your team's working and you want me to show you something, feel free to reach out, and of course I will do that. Okay, so one more thing before we're done today. And when we're looking at these probability distributions, we call them a normal probability distribution, right? And we went back to the empirical rule. We talked about the empirical rule with it. And with that, we said, okay, well, the empirical rule is used for a bell-shaped, symmetric shaped, or normally distributed data, right? And that's exactly what the normal probability model or the standard normal uses, okay? It's normal, so it's normally distributed. So I want to talk to you about assessing normality today. And all this is how to tell if we have data that's normally distributed. So the thing you're going to ask yourself is my data normal? So I say normal all the time, but it's same thing as normally distributed, whatever. So I don't always just say it the same way. So is my data normal? That's what I need to ask myself. Well, I have a couple of ways to tell. So sometimes it's hard when we're just looking at a sample or population to see if they're normal, but we have a couple different ways. So the first way, I'm going to say yes, normal, if the histogram of my data is bell-shaped. Right? Because if it's bell-shaped, then it's symmetric and it should look pretty normal. Okay, because normal is symmetric, bell-shaped. So that's one way. Another way is if we're told. So if we are told that it is normal. So like the example I gave you yesterday, I just came right out and said, you know, we looked at the student heights, they're normally distributed. I told you that. So we didn't have to go and find it out. We didn't have to figure it out. But we have a third way today we're going to talk about. So let's just make a little note. So what if we cannot tell from the histogram? And we are not told. Then we will use a normal probability plot. And a normal probability plot is just an NPP. I never write it out, normal probability plot, after this. And I never even say it. I just say NPP. That's a normal probability plot. And I want to talk to you about this plot and what it looks like and how we can use that to see if our data is normal. Okay, so I'm going to give you some information about the NPP first, and then we'll get back to number 3 on here. So an NPP looks like a scatter plot. Sorry, I'm on an angle a little bit there. Okay, it looks like a scatter plot. So remember back in chapter 4, we had scatter plots. That's what it looks like. It's not a scatter plot, something a little different, but it looks just like it. Okay, and what an NPP is a graph that plots observed values. Now remember what observed values, these are my actual data values that I collected, okay? This is what I actually have. Observed values versus, so here it is, this is why it's like a scatter plot, versus normal scores. Now what the heck does that mean? The normal scores, right? So normal scores, all these little notes in here. Normal scores are just what I expect to get. So these are expected z-scores based on our data that we have already. Assuming it is normal. So what I mean by this is that based on our data, we can get like a mean, a standard deviation, right? And we're not going to do this by hand. Our technology is going to do this for us. But it can tell what something should be normal based on the average and the spread of the data, what it should be, okay? And what it does is that it calculates these expected z-scores and it puts them against our observed values and it plots them. So what happens is if we have, this is my number 3. So if the NPP is fairly linear, or I'll say fairly close to a straight line, or we're saying linear, then yes, normal, okay? So 1, 2, and 3. So if the histogram's bell-shaped, or if we're told it's normal, or we could check our NPP and see if it's linear. So like I said, our calculators can do this for us. You're just going to put your data values. You have to have your data values in order to do this. So you would put your data values in a list, and then you could follow the directions. It's on the sheet, both sheets, the team assignment and the separate posting of the directions. And all you're doing, it's a visual. You're just looking at this plot to see if the dots line up. Okay, it doesn't have to be a perfect line. It's fairly linear, okay? Fairly close to a straight line. So this is one of those things where it's not just cut and dry, right? Someone might look at it and say, I think it's pretty straight, and the other person might say it's not really. And everyone's a little different, but I think most of the time we agree on what's fairly linear and what's not. And same with Minitab, you're going to just put all your values in a column, and then you ask for an NPP. And it's just a visual. Now, if you use Minitab, you will get some values and some numbers in the output that go with the picture. You're just going to ignore those right now. That's something we look at when we are in Stat 2. But in Stat 1, we don't even use those. We just use the visual of the graph. Okay? So that's assessing normality. So now we have 3 ways of telling if we can have normality. Why do we need to do this? Well, if we are going to use a normal probability model to calculate probabilities or percentiles, we better make sure that our data is normal, right? We don't want to use a model that doesn't correspond with our data set. Right? So we only want to use a normal probability model if we have normal shaped data. So we always want to make sure of that. So that's something that we're going to start doing, and we'll start moving forward with all of that.